Hello and welcome to AP Physics C, Electricity and Magnetism, the AP Daily videos. Today we are on topic 9.2, electric potential. This is daily video 2. In this video, we will explore the relationship between electric potential and electric fields. My name is Michelle Strand. I'm joining you from Washington, D.C. I am an Einstein Fellow on Capitol Hill. So let's warm up. So it's important to know how the electric field and the electric potential are connected. And on the formula sheet, we have these relationships that E sub x is equal to the negative derivative of potential with respect to displacement. So minus dV dx, and delta V, which is the change in the electric potential, is equal to the negative integral of the electric field E dot dr, because we are moving from vector to scalar quantities. The derivative integral relations are very similar to what you find between velocity and displacement. The velocity is the derivative of position with respect to time, and the displacement is the integral of the velocity time function. So you might wonder, why do we have negative signs here? So the negative signs here are because of how the electric field flows. It always flows from a high to low potential. So if I calculate a change in potential, and I always do final minus initial, I'm going to get a negative value. So the negative in the equation then will take care of that. So let's look at an example. So here's a look at an example. We're dealing with symbolic expressions. So we have an expression for E sub x is equal to 3x squared plus 2x, and we want to derive an expression for V sub x. And so if we remember, V sub x here is going to be equal to the negative integral of E dot dx. So I'm going to put this negative sign out here and integrate each of these parts of the expression. So 3x squared becomes 3x cubed divided by 3. And the 2 becomes 2x squared divided by 2. And then keep in mind that we need to add in this constant of integration. And the constant of integration is always the initial value of what you're looking for. So this is really going to be just that initial potential. So if I simplify these expressions here, I get that Vx is going to be minus x cubed minus x squared and minus V0. So let's practice. So here again, we have an electric field function, E sub x equals minus 2x plus 4. And I want to calculate the electric potential at x equals 2 meters if V equals 0 at x equals 0. So I am going to find the electric potential. V sub x is minus, again, E dot dx. Just like in that last piece, I need to know that initial condition, that V0, and here it is 0. So I'm not going to have to worry about a constant of integration. So I have negative, and then I'm going to take the integral of each of these parts. So I have minus 2x squared over 2, and then I have plus 4x. And I don't need the constant because I know it's 0. So the 2's cancel here, and distributing the negative sign, I get x squared minus 4x as my potential. So if I want to know what it is at x equals 2, I just plug in a 2 where x is. So this is going to be 2 squared minus 4 times 2. So 4 minus 8 gives me minus 4 volts. We also want to take a look at one where we're given the potential function. So V sub x equals 3x cubed minus 2x plus 5. And I want to calculate the electric field at x equals 2 meters. So here the electric field is minus dV dx. And this is the electric field in that x direction. So I'm going to have that negative sign. I'm going to take the derivative of this expression. So I'm going to get a 9x squared minus 2, because the derivative of a constant is 0. So distribute that negative sign. That's going to be minus 9x squared plus 2. And x equals 2 meters. So I'm going to plug in 2 squared plus 2. So this is negative 36 plus 2, which is going to give me negative 34. And the electric field can either be in newtons per coulomb or in volts per meter. So what should we take away? Couple of things. That electric field and electric potential are related to each other, despite the fact that one's a vector and one's a scalar. They are connected by a derivative and an integral. And that there is that negative sign in both equations because of how the electric field moves from high to low potential. So it's sort of setting things right by the fact that delta V for the electric field is always going to be negative. Thank you. I hope that was helpful and have a great rest of your day.